So we continue on the journey. Today we're going to be talking about the true nature of carbohydrates. We've been drawing them in Fisher projections. As a summary, we can generally classify this sugar to the left here as an aldo, coming from that part, and as a hex coming from the 6 carbons, and a ose because it's a sugar. And then we look at the very last stereocenter, and that is of configuration D. So this is a D-aldohexose. Now in nature, in our bodies, they tend not to exist in this open chain form. They tend to exist in this closed chain form. And so what we're going to do is revisit the hemiacetal chemistry. And essentially what we're going to do is just have this hydroxyl attack that carbonyl there, and we get a closed form. Since it is a 5-membered ring, it is referred to as a pyranose. So this is a pyranose. We'll talk a little bit more about the mechanics of that, but as a side note, when we attack this carbonyl with one of these hydroxyl groups of the sugar, we can attack the carbonyl from the top and push the OH down, or we could attack it from the bottom and push the OH up. And to simplify things in this chapter, what we'll do is if that OH is down, we refer to it as the alpha anomer. If it's up, we refer to as the beta. Now we find out which anomer by looking at what's referred to as the anomeric carbon. The anomeric carbon is highlighted here. It's the special carbon. It's the one that is sharing a bond with 2 oxygens. And so what we need to do is identify the anomeric carbon, and then if we find the OH down, we refer to it as alpha. If we find the OH up, we refer to it as beta. Now that's a oversimplification of how you determine alpha and beta, but for these times that will suffice for right now. So the question is, well, how do we draw Haworth projections? And that is the name of these cyclic forms. So what we do is you take the structure of the sugar in the Fisher projection and you just lay it down. What I say is you take a little lumberjack here with this little axe, and you chop down the sugar and it falls to the right. Now, when it falls down, you notice that the highest oxidized group is to the right, and that's important. And what we do is we just start wrapping things around. So in between this bond 2 and 3 right here, that's going to be the bond that we're going to keep straight. And we'll kind of tuck that one back, and then we're going to wrap all these around this direction here. And so you can see what that would look like if we just started wrapping things around. Now this stereocenter right there is what determines if the sugar is D or L. Okay, it's in red here. So I'll put it in red over here. This OH right there. Since it's down, this is a D sugar. But that's going to be the alcohol that actually closes up in the Haworth projection to make the pyranose. So to do that, what we've got to do is actually rotate that OH up so it's in the plane of the carbonyl. And you can see that down here. So what we've done is this OH that's in red right here is the same OH that's here, same OH that when it fell down, it's here. When we wrapped it around, it's here. And now that we've rotated it, it's here. Notice what that does to this group right here. It pops that CH2OH up. Okay, so you're going to notice this common feature, that CH2OH pops up, which means that this is a D sugar. And it's a D sugar because if we trace it backwards, it was originally pointed down and down or to the right in a Fischer projection. So how does hemiacetal formation work? Remember back to the carbonyl chapter, we protonate the carbonyl and then simply the alcohol attacks. And then we deprotonate the attacking OH. So once this OH attacked here, it would actually have a positive, and then a base comes and deprotonates it. And again, it can attack from the top or the bottom. Now what we can say is that this is a D sugar, and this is also a D sugar. And notice the arrangement between that CH2OH and that OH there. We can say that they are trans to each other. And notice the A there, it's an alpha. And here, these are cis. And if you speak German, that's known as the S set or the double S. So cis, or the beta anomer, has this OH and that CH2 on the same side. And that will always be true for D sugars. For D sugars, when this is up and you draw the Haworth projection, which is this form right here, if this is up, that is a beta sugar. If this is down, that is an alpha sugar. And again, that will always be true if you draw them in this form and you're using D sugars. Which means if you're using L sugars, then things change. But luckily, we're not going to tackle that at this time. So again, how do we do this? Here is the process. You take the Fischer projection. So off to the left, we have glucose, which is one of the sugars that you should know by memory. And we drop it down to the right. Now you'll notice, here's the carbonyl, and we're gonna place that right here at the very kind of corner of this hexagon. So that position right there is where the carbonyl is going to be. And then what you do is you notice that this one is to the right and it's down. This one's to the left and it's up. This is to the right and it's down. And this is to the right and it's down. Now notice the OH that is orange, that is the last chiral center, and that's the one that determines if it is D or L. Now they don't have a fun name for it like they do anomeric carbon or all the other fun names. Well, usually in class we decide on a fun name to call it because again, this is the carbon that determines if it's D or L. So in the past we've decided on the Stephan center or the sexy center. Since I don't get your vote, I think we're going to go with the Stephan center this year. So this Stephan center right there, notice it's down, but again, it's going to be the OH that closes. So we've got to rotate it up. So when we redraw it, this goes up, and the OH is now in a position where it can attack that carbonyl. Once it attacks that carbonyl, it could attack from the bottom and force the OH up, which would give us the beta anomer, or it could attack from the bottom, or sorry, attack from the top, forcing the OH down, giving us the alpha anomer. So in the end, the convention for drawing sugars is we're going to map them onto this structure right here if we're going to close it up in the pyranose form. And so if we're using aldohexoses, specifically D-aldohexose, this is going to be the generic form for a D-aldohexose in the pyranose form. In fact, I believe it's called D-aldohexose D-aldo or D-hexanpyranose is the name for that when it's in the closed form. Now, if the OH is up in this form, we refer to it as the beta anomer. And if the OH is down, and I'm just going to simplify this, you'll never have two OHs off that, but for illustration, if it's down, that would be the alpha anomer. And that, again, that is always true for these D-aldohexoses when we draw them in the pyranose form. And again, these are known as Haworth projections. So here's an example here. We've got mannose. This isn't one of the sugars that we were expected to memorize, but if I give you that structure there on the left, you should be able to draw the Haworth projection on the right there. But I need to tell you which anomer it is. So if we want to draw the alpha anomer, we would go and draw the OH down as shown. If the instructions said draw the beta anomer, we would draw the OH up. And then what we want to do is add the rest of the OHs. So let me color code some things. This carbon right there turns into that anomeric carbon right there. So your carbonyl will turn into your anomeric carbon. So always be able to find your anomeric carbon and understand that in its previous life, that anomeric carbon was a carbonyl. And once we find that, what we can do is we can see, okay, well, the next carbon over is going to have an OH. And since that OH is off to the left, if we drew that lane down, that OH would be up. The next OH in the blue box is also to the left, which means it's also up. The next OH is the one that is down, and so it is shown down, or sorry, it's to the right, so it would be down. And then what we've got is our Stephan center right there, the one that determines if it's D or L. Now this is kind of hard to see, but it's that carbon right there. And you may say, well, where did the OH of it go? The OH of that Stephan center is now connected right there. And then what we have is the rest of the CH2OH is popped up since it's a D sugar. So let's do the same for the beta anomer. And really, everything is the same other than the anomeric carbon. We draw the red OH up, we draw the blue OH up, we draw the black OH down. The Stephan center, or the one that determines if it's D or L, is right there, which causes that CH2OH to pop up. And the oxygen of the center that determines if it's D or L is right there. So you can check our answers below, and you can see that we did it properly. So you should have the skill of taking sugars and drawing them in the appropriate Haworth projection given instructions on whether it is an alpha or beta anomer. Now, some sugars don't have enough carbons to form a 6-membered ring, and so they may form 5-membered rings, and these are known as furans, and in the case of sugars, they're known as furanoses. Now, either you could not have enough carbons to form a 6-membered ring, or we haven't talked about this yet, but ketoses. Ketoses can also undergo this reaction. So this carbon in green, this is a ketohexose, specifically a D ketohexose. And notice that we don't have the aldehyde. We've actually moved the carbonyl 1 carbon in. So if we use that Stephan center to close up, our ring is going to be 1 less. It will now be a 5-membered ring, which again is referred to as a furanose. So same process, we just lay this down on its side. Anything to the right is going to be pointing down, anything to the left will be pointing up. And then we take an alcohol and attack that protonated carbonyl. and it will turn into a cyclic hemiacetal. Now notice there's a very important difference that we see here between what we looked at when we had aldo sugars. And that key difference is off of the anomeric carbon, okay, that carbon right there. Remember, the anomeric carbon is the one that's sharing a bond with two oxygens. That anomeric carbon, instead of having an H off of it, like it does in an aldose, it has a CH2OH. So you can always identify a keto sugar when it's in its cyclic form. You just look at the anomeric carbon and see if there's a CH2OH, and then you know it was a keto sugar. So just as examples, I'll explain a little bit more about them at the bottom, but there's my anomeric carbon. I know that because it's sharing two oxygens, and it has a CH2OH off of it. So that came from a keto sugar. This one here is the anomeric carbon because it's sharing two OHs, and it has a CH2, so that came from a keto sugar. This one right here, there's the anomeric carbon because it's sharing two oxygens, and off of that anomeric carbon, there's a CH2OH, so I know that came from a keto sugar. Right here, that's the anomeric carbon because it's sharing the bond to two oxygens, and it has a CH2OH off of it. So I know that it came from a keto sugar. So let's see if that holds up. I find the anomeric carbon here. It's sharing the bond with two OHs, and it has an H off of it. So I know that came from an aldo sugar. Okay, again, sharing two oxygens. There's the anomeric carbon. It has a hydrogen, so it came from an aldose sugar. Okay, so you can form 5-membered rings. So if I use the Stephan center to close up right here, I'll color code it to match the top. If I use that carbon right there to close up with the carbonyl, I'm going to get a 5-membered ring. Now this is a different sugar than the one up above. In fact, this sugar down in the red box right here is actually one of the sugars that you should have memorized. Okay, so this is known as fructose. Oh, sorry, not fructose. Sorry, this is fructose up here. This is the one that you should have memorized. So I've got a little error. Nice thing is I can fix that error on the fly right now. I need to make these sugars match right here. There we go. So we're going to put the H there and the OH right there. Okay, so if we take that sugar, which is fructose, and we close up with the OH that is in yellow, would get a 5-membered ring. But we could also close up with the OH that is in orange. And if we count from the orange OH to our carbonyl, that's 1. Let me get a different color. 1, 2, 3, 4, 5, 6. So on these keto sugars, you can get 5-membered ring, furanoses, or you can get 6-membered ring, pyranoses. Now pyranoses look odd, and they look odd because at this center right there, there's not that group sticking up. Well, if we don't have a group sticking up here, then we know that we didn't close with that Stephan center. In fact, we closed in this case with the very last OH. Okay, this OH is this very last OH. So then the question is, well, where is our Stephan center? The Stephan center right here is right there. Now that OH is pointing down, which means when we would have drawn it in the Fisher projection, it would be pointing to the right. So in this case here, to figure out if it's a D or L sugar, I can't just look at this position here, or here, or here, because again, like I mentioned previously, if that CH2OH is sticking up, it's a D sugar. In these keto sugars, what's interesting is we're not closing with the Stephan center, we're closing with the last OH. So to identify if it's a D sugar, you have to go to the last chiral center, which is right there. And notice it's down, which means that it would be to the right in the Fisher projection, which means that this is a D sugar. and this is a D sugar. Okay, so that's an important skill. Now, just to let you know, we see these a lot less. The two main important skills would be able to draw aldose sugars in their pyranose form and ketose sugars in their furanose form, or their 5-membered ring. Those are the more common sugars that we find, these 5-membered rings. Okay, these are biologically important. We're just not going to deal with them as much, but that is a possibility. Okay, so like I said, in nature, they tend to be in their cyclic forms. So if we have D-fructose, and we actually go and say, well, what does it exist at in nature? We've got two different possibilities for fructose. We've got a furanose form and a pyranose form. Well, that's not the only possibilities we have. We also have the alpha anomer and the beta anomer. Now, we're not showing you all possibilities here. To identify the anomers, again, what I want to do is look at this OH here, that's up, so we would identify this as the beta anomer. If we wanted to draw the alpha anomer, we would just switch these two positions here. The next one down below is also a beta anomer. And again, if we wanted to switch it to the alpha anomer, we would just switch those two positions. So we're only showing you really the beta anomers. Now, there's a reason for that, and that is these are the most common. So let's look at the possibilities. So remember, we've got 4 possibilities here. We've got the alpha, second, let me match this up a little bit better. We've got the beta pyranose. We've got the alpha pyranose. We have the beta furanose, the 5-membered ring. And we've got the alpha furanose. So actually, if you just threw fructose in water, it would actually, you would have 5 different products in there. You'd have the open chain, but there's not very much of the open chain, only about 0.7%, which lets you know that sugars tend to exist in their cyclic forms and not their open chain form. The most common is actually the beta form, and that's why they're showing this beta anomer here. That is by far the most common. You get about 2% of the alpha, and again, to get the alpha, we would just switch the orientation of those 2 positions there. There is a decent amount of the furanose form, the 5-membered ring. Again, it favors the beta configuration, or the beta anomer. And again, to get the alpha anomer of this, which is about 5%, you would just switch those 2 positions. Now, this is just in water. So this is without anything favoring one product over the other. This is just the equilibrium that these would establish in water. Now, in nature, nature has a way to pick which form and which anomer it prefers. So you don't need to memorize these, because if I wanted you to do this, I would say draw the alpha pyranose form, draw the alpha furanose form, draw the beta furanose form, or draw the beta pyranose form. Just interesting to know that they are all different in concentration. And I'll leave it up to you to try to start to figure out, why would I have different amounts of these? What is making the beta pyranose the most favorable form? And also, why would the beta furanose be of significant contribution? Why does the alpha pyranose, why is it so small? Why is the open chain in such small concentration? All good questions. Okay, so what we need to do is just brush up on some of our vocabulary here. So the structure of monosaccharides, they tend to exist in cyclic forms. And when they exist in these cyclic forms, we have 2 different ones, the pyranoses and the furanose. And in the pyranose form, we can have the alpha anomer and the beta anomer. I just realized I have another mistake on here, so we'll correct that. It can exist in the 5-membered ring, which we all know is a furanose. And in the 5-membered ring, it can exist as the alpha anomer, again with the OH at the anomeric carbon pointed down, or the beta anomer with the OH pointed up. And again, we can run with that as long as we're playing with D sugars and we draw them in this form. And what I mean by that is don't start making up your own rules for drawing these and start drawing stuff like this for sugars. Okay, these are all bad. And everything I'm telling you right now may or may not be true if you decide to blaze your own path and draw the structures non-conventionally. So there is a convention. When we draw furanoses, we draw the OH at the top. When we draw the pyranoses, we have a flat top on our hexagon, and that OH is in that top right corner. So check, that's the proper form, and check, that is the proper form. Again, if you decide to do things differently, all bets are off in what I am telling you. So again, if we use the standard convention, we can always say that this alpha anomer will be down and this will be up as long as we're using D sugars. We're using L sugars, everything flips. But nature prefers D sugars. So, okay. Now, as I said, when we put the open chain in solution, it tends to close up, and form these cyclic structures. Now, we gave you the example in the distribution of products for fructose, so let's look at glucose. So we throw glucose in water, and we just happen to get a very, very small amount of the open chain, 0.02%. So by far, this one dramatically prefers the closed chain form. And you can see the two options that we have. We have the beta glucose. So we've closed up in the beta anomer, and we get 64% of that. But about a third of it is in the alpha anomer. So there's not a lot of stability. Oh, I just gave away the key to my previous question. It's stability that's driving this. So the fact that we get a little bit more of the beta glucose means that it is slightly more stable. Now, if I happen to isolate or go and buy pure beta D glucose, I went to the store and said, just give me some beta D glucose. And then I dissolved it in water and was trying to eat it because I heard it cures coronavirus, I would be in trouble. First of all, probably because it doesn't cure coronavirus. And second, as soon as I put this pure solid in water, what's going to happen is it will re-equilibrate. It will undergo this equilibrium reaction where it will open up to the open chain form, and then some of it will go to the alpha anomer. And it will reposition itself so that you have this 36.02, 64% distribution. Even if I started with pure solid beta D glucose, as soon as I put it in water, it will re-equilibrate. It'll take some time, but it will. And that process is called mutarotation, the interconversion of one anomer to the other. So if you have a solid pure anomer and you put it in water, it will mutarotate. It will convert or distribute between the alpha and beta. Now, we're not going to spend a lot of time in being able to predict why one anomer is more stable than the other. But for glucose right here, we can use skills that we already know and come up with a pretty good answer of why that beta D glucose is the most stable anomer. And I'll give you a second to think of what skill we could use to predict why beta-D-glucose is the most stable anomer. Why I sit here in my chair. Yeah, so we could use chair conformations to predict. And so if we drew the chair conformations of alpha-D-glucose and beta-D-glucose, we will see an interesting difference between those structurally. Now, this isn't always true. Sugars are a little bit more complex. There's even what's referred to as the anomeric effect. We're not going to get into that, but in the simplest case, we can look at the chair conformations, and it will explain why the beta anomer is more favorable. And you're going to have to wait because my computer just froze again. I know you were dying in anticipation, but this is what I wanted to show you. Actually, glucose drawn in the chair conformation. So if you remember from the previous slide, we had, actually I can't remember. There we go. We had roughly 36% of this and 64% of that beta anomer. And so the answer's in the difference. What is different between this alpha anomer and the beta anomer? We know the beta is slightly favored. So what would favor the beta anomer? Well, if you're having troubles, I will point out the difference. The difference is simply the configuration of the OH at that position. And hopefully you're just screaming in anticipation or telling me to get on with it, saying that, hey, glucose, when it is in the beta anomer, has all the groups equatorial, and we know that having the groups equatorial is more favorable. It's interesting that these anomers actually have different solubilities, so you can actually isolate pure anomers. So if we wanted to isolate the alpha anomer, we would saturate the solution and cool it below 98, and we would preferentially get a mixed or the pure alpha anomer. Or we would saturate it and then keep the temperature above 98 degrees, and the beta anomer would preferentially crystallize out. But notice, if we mix it in water, we will actually get a mixture of alpha and beta anomers. And so what that process is called, again, is the mutarotation. So something that's interesting, if we look at the optical rotation here, the pure beta anomer, we're rotating positive here. Now, if we just change one stereocenter there, and we just have the alpha anomer, all we've done is change the configuration of one stereocenter, and you can see that its pure form actually rotates light a lot more to the right. Now, the relationship between these compounds, where they only have a difference at one stereocenter out of all the other possible stereocenters, is referred to as epimers. We'll talk a little bit more about epimers later, but epimers is another vocabulary term that you should know, where compounds differ only at one center of chirality out of all the other possible ones. So, as a side note, I told you before that glucose rotates light to the right, and it is known in medical settings as dextrose. If you ever watch a good medical show, they'll say, hey, get this person some dextrose. And really what they're saying is get some glucose in the pyranose form. And since it's in solution, you're actually giving them a mixture of 64% beta and 36% alpha anomer. So you could imagine a medical professional saying, hey, this person needs some nutrition. Get them a mixture of 64% beta anomer glucose, or glucose in the pyranose form, and 36% alpha glucopyranose. Very confusing, just easier to say get dextrose. So we're going to leave it there. We're talking about, or anyway, in summary, we'll just leave it there. As mentioned, why beta D glucose ends up being more favored is all the groups are equatorial. So you should be able to draw these structures. Again, you need to know a couple sugars. We told you to know galactose and glucose and fructose and ribose. And so we could take one of those sugars, you'd pull it from your memory, and then I'd say draw it in the furanose form, specifically the alpha anomer or the beta anomer. Now, I could also have you draw other sugars. I would just have to give you them as a Fisher projection. So galactose is one of those that we had you memorize. And so I could say, hey, draw galactose in the alpha form. And to get all the points, it would look like this. We'll leave it there. The next sections will include reactions of monosaccharides. And luckily for us, those are all repeats of reactions that we've already seen before. We'll talk to you soon.